Hi, here is Mark Dubois from HaroTech. I am presenting here a new capability introduced in version 2.1 of the Haro 3D library, sharing of holograms between multiple HoloLens using a common coordinate system. The robot demo that was presented in previous videos was modified to demonstrate this new feature of the Haro 3D library. The code used for this video will be available in National Instruments 3D Vision Virtual Group. The link can be found in the description of this video. This new feature consists in giving the ability to one HoloLens user, the primary HoloLens, to show holograms to other HoloLens user, secondary HoloLens. The holograms can be shown in the same physical location for all HoloLens. The connection mechanism is illustrated here. First, the LabVIEW application is started on a separate computer. Then, a first HoloLens connects to the LabVIEW application. The first HoloLens to connect is the primary HoloLens. Then the following HoloLens to connect would be a secondary HoloLens. All subsequent HoloLens that connect to the LabVIEW application are also secondary HoloLens. If the primary HoloLens terminates, connections to all secondary HoloLens also terminate. For the current demo, only two HoloLens will be used. I will be wearing the primary HoloLens. The secondary HoloLens is installed on a tripod and is looking at the holograms that I will be handling using the primary HoloLens. This demo will show video feeds from both the primary and secondary HoloLens. Let's have a look at the code. The front panel of the modified VI is shown here. The main difference is the presence of two indicators giving the IP addresses, or network names, of the primary and secondary HoloLens after they connect to the LabVIEW application. Let's have a look at the block diagram now. Among the modification of the block diagram, a new user event was added, Receive Anchor. An anchor is a point defined in the HoloLens space, not by the coordinate system, but by features of the 3D representation of the room as mapped by the HoloLens. The anchor is created when a new origin is defined by the primary HoloLens and then shared with the secondary HoloLens. Once defined, the primary HoloLens sends the anchor as a user event to the LabVIEW code. The anchor is typically tens of megabytes, so a data value reference is used to store it. The DVR is deleted if already present. Once received, the anchor is sent to the secondary HoloLens using the corresponding VI. Let's begin the demonstration by running the VI. Then, let's start the Haro 3D app on the primary HoloLens. Once the primary HoloLens is connected to the LabVIEW application, its network name appears on the front panel of the VI. It is important to start the secondary HoloLens only after the primary HoloLens has connected. The network name of the secondary HoloLens also appears on the front panel. After connecting, the robot to be loaded is selected from the primary HoloLens. The mesh files of the robot are loaded within the LabVIEW application and transmitted to the primary and secondary HoloLens. By default, the robot is displayed in position 0, 0, 0 of the HoloLens coordinate system, which are the physical positions of each headset when the Haro 3D app was launched. A common coordinate system is shared between both HoloLens by first selecting a point on a surface mapped by the primary HoloLens. Start mapping.
Mapping started.
Stop mapping.
Mapping stopped.
The point where the new origin is moved becomes the origin point of the coordinate system of the primary HoloLens. The robot hologram is moved to that point and an anchor is created and sent back to the LabVIEW application. As soon as the definition of the anchor is transferred and recognized by the secondary HoloLens, the robot hologram is moved to the new 0, 0, 0 point, which should be the same physical locations for both HoloLens. Any action from the primary HoloLens on the robot is now also observed by the secondary HoloLens. For example, changing the scale of the robot from a default value of 1/4 to approximately 50%. Notice that here the choice was made to scale the robot only when the air tap position is released, to prevent any communication problem due to the excessive redrawing of the robot. The axis of the robot can be moved using hand gestures. The axis movements can be observed by secondary HoloLens exactly as they are perceived by the primary HoloLens, but from a different point of view. Another feature that was added with version 2.1 of the Haro 3D library is the access to the absolute position of the hand during hand gestures. Using this new feature, a capability was developed in the LabVIEW application to draw lines in the air. This capability was called 3D markers. Notice that the information provided is the absolute position of the palm and not the fingertips. Also, when the hand gets near the edges of the zone of hand detection of the HoloLens, the hand position gets very inaccurate. This is why it is better to make small hand movements, try to keep the headset leveled when using the 3D markers, and release the air tap while the hand is well within the detection zone of the HoloLens. To see the actual size of the robot, the scale is reset to 1. The whole setup is scaled, including the 3D marker. Do not hesitate to leave question, comment, feedback in the comment section of this video, in National Instruments 3D Vision Virtual Group, or directly at harotech.com. Thank you for watching.